What if I told you that there's a single, simple rule that underpins all of physics? And I don't mean just some of it, I mean all of it. We're talking classical mechanics, electromagnetism, even quantum theory and general relativity. It sounds impossible, right? Well, let's dive in.
I mean, just think about that for a second. It's a breathtaking claim. The idea that everything we know about the physical world, every single law we've ever discovered, could all be boiled down to one single foundational principle. This isn't just some clever mathematical trick. It's a really profound statement about the very nature of reality.
So what is it? What single idea could possibly be powerful enough to unify all of physics? Well, the quest to find it doesn't start where you might think. Not with black holes, not with quantum fields. No, it starts with a surprisingly simple problem. A puzzle, really, that was posed centuries ago.
Okay, so here's the puzzle. Imagine you want to get a small ball or a mass to slide from a point A to a lower point B. The question is, what shape of ramp or path will get it there in the absolute fastest time? This is famously known as the Brachistochrone problem, or the problem of fastest descent. Now, your first instinct, like mine, is probably wrong here. You'd think, well, the shortest path between 2 points is a straight line, so that must be the quickest. But it's not. Think about it. If you dip the ramp down at the beginning, the ball gets a huge burst of speed early on. It gets a running start. So even though it travels a bit farther, it covers that distance so much faster that it ends up winning the race. The real question is, what is the perfect curve?
Even the great Galileo himself took a stab at this and guessed it was the arc of a circle, but he was wrong. Fast forward to 1696. A brilliant, but let's say very proud mathematician named Johann Bernoulli poses this problem as a public challenge. He was basically hoping to prove he was the smartest guy in the room, especially smarter than Isaac Newton. Well, Newton, who was busy working at the Royal Mint, got the challenge, was apparently pretty annoyed to be bothered with it, and then solved it in a single night.
And here's the best part. Newton submitted his solution completely anonymously, but his genius was just so unique, so powerful, that it was like a signature. When Bernoulli saw the solution, he knew immediately. He famously said, "I recognize the lion by his claw." He knew that only Newton could have come up with such a masterful answer.
So how did Newton solve it so fast? What was the secret? Well, the breakthrough didn't come from the world of sliding masses and gravity at all. The clue came from a totally different area of physics. In fact, Bernoulli's own solution was inspired by the way light behaves.
You see, back in the 1650s, a guy named Pierre de Fermat discovered something incredible about light. It turns out, light doesn't always take the shortest path, it takes the fastest path. You've seen this. When a ray of light hits water and bends, it's not taking the most direct route, it's taking the path that will minimize its travel time. This was the first major clue that nature might be, well, lazy, that it follows optimization principles, always trying to do things in the most efficient way possible.
And this is where Bernoulli's genius really shines. He connected these two completely separate worlds. He imagined the falling mass as if it were a ray of light. And as the mass falls, it speeds up, right? So he imagined the light ray traveling through different layers of glass, each one denser than the last, causing the light to speed up in the exact same way. So if you could figure out the path the light takes using Fermat's principle, you've solved the original problem. It's an absolutely brilliant conceptual leap.
And the answer? It wasn't a straight line, it wasn't a circle. The solution was a cycloid, which is the beautiful curve traced by a point on the rim of a rolling wheel. Just an astonishing result that proved that these two completely different fields of physics, mechanics and optics, were somehow speaking the same fundamental language.
But this was just the beginning. It led to an even bigger question. If light minimizes time, is there some other, more general quantity that everything in nature minimizes? This incredible idea led to the creation of the principle of least action.
So in the 1740s, a French thinker named Pierre-Louis de Maupertuis proposed this new quantity he called action. He defined it, roughly, as an object's mass times its velocity times the distance it travels, all summed up over its entire path. He claimed that this action is what nature truly tries to keep as small as possible. The path an object actually takes, he said, is the one that has the minimum possible action.
His idea was, well, revolutionary, but the reaction was brutal. I mean, he was publicly attacked and ridiculed. His former friend, the famous writer Voltaire, wrote a whole pamphlet just to make fun of him. You see, the problem was, Maupertuis's principle was based more on intuition and philosophy than on solid, rigorous math. But this is where the story gets really cool, because it shows how science works. Maupertuis had the initial spark of genius. Then the legendary mathematician Leonhard Euler came along and put the whole thing on solid mathematical footing. He showed it worked perfectly for things like planetary orbits. And finally, Joseph-Louis Lagrange perfected it, inventing a whole new branch of math called the calculus of variations to create a bulletproof general proof.
Today, the principle usually takes a slightly different, even more powerful form thanks to William Rowan Hamilton. Instead of minimizing momentum over distance, Hamilton's principle says that nature minimizes the difference between kinetic energy, that's the energy of motion, and potential energy, that's stored energy, integrated over time. This is the modern version you'll find in basically every advanced physics textbook.
Okay, I know this might all seem incredibly abstract, but trust me, this new way of looking at the universe was a complete and total game changer for physics. It gave us a much more powerful and elegant way to describe how everything works.
So you might be thinking, hold on, I learned F equals ma in high school. It's simple, it works. Why would anyone bother with this super complicated action stuff? And that is a perfectly fair question. Why invent this whole new complex framework when the old one seems to work just fine?
Well, it really comes down to a difference in perspective. Newtonian physics is all about forces, pushes, and pulls. These have a direction, so we call them vectors, and they can get complicated fast. Lagrangian physics, on the other hand, is all about energies, which are just simple numbers or scalars. So instead of asking, what's the force on this object right now, it asks a much bigger question. Out of all the possible paths from A to B, which one minimizes the total action?
And this energy-based approach is unbelievably powerful. Take something like a double pendulum, a pendulum hanging off of another pendulum. Trying to solve that with Newton's F equals ma is an absolute nightmare of forces and angles. But with this method, you just write down the kinetic and potential energies, which is easy. You plug them into the Lagrangian machine, turn the crank, and out pops the correct equations of motion. It just works. It's a unifying principle and a problem-solving superpower all in one.
Now, one quick but important clarification. We've been calling it the principle of least action, but technically, physicists call it the principle of stationary action. All it really means is that nature chooses a path where the action is at a flat point. It could be a minimum, but it could also be a maximum or a saddle point. For our purposes, it's almost always a minimum, but it's a fun little detail to know.
So we end up right back where we started. This one single rule, that nature follows a path of stationary action, is the foundation for all of classical physics. But its reach goes even further, stretching deep into the strange world of quantum mechanics, where particles seem to explore all possible paths at once. It really leaves us with this huge, provocative question. Is this elegant principle just a useful tool, or is it telling us something truly fundamental about the source code of the universe itself?